Dependency injection is a technique where we delegate instantiation of dependencies to an inversion of control container. In our case, this IOC container is the Nest.js runtime system itself. Nest.js handles all of the heavy lifting here, instead of trying to achieve dependency injection ourselves. Essentially, when we ask for a dependency in a class constructor, Nest.js handles and retrieves the object back to us, along with any dependencies it might require, and so on and so on. Let's take a look at an example in our own code and dive into how it all works. In our coffees controller, when we are using coffee service and injecting it here in our constructor, what exactly is happening in Nest.js under the hood to make all of this work? Well, there are 3 key steps in the dependency injection process that make it all happen. First, in our coffee service, the injectable decorator declares a class that can be managed by the Nest container. This decorator marks the coffee service class as a provider. Second, if we jump over to our coffees controller, we can see we are requesting the coffee service in our constructor. This request tells Nest to inject the provider into our controller class so that we may be able to utilize it. Lastly, Nest is aware that this class is also a provider because we've included it here in our coffees module, which registers this provider with the Nest inversion of control container. That's how it all works in our code itself, but now let's dive even deeper to see what Nest does. When the Nest container instantiates the coffees controller, it first looks to see if there are any dependencies needed. In our case, there is one, the coffee service. When the Nest container finds the coffee service dependency, it performs a lookup on the coffee service token, which returns the coffee service class. Assuming this provider has a singleton scope, which is the default behavior of injectable providers, Nest will then either create an instance of coffee service, cache it, and return it, or if one is already cached, it will return that existing instance. We are simplifying everything a bit, but hopefully this all helps illustrate the point. Analyzing our codebase for dependencies is quite the complex task that Nest handles for us, and it all happens during application bootstrapping. This dependency analysis, or creating the dependency graph, is transitive. In this example, if the coffee service itself has dependencies, which it does, those dependencies need to be resolved as well. The dependency graph ensures that dependencies are resolved in the correct order, or essentially, that they are resolved from the bottom up. This mechanism relieves the developer from having to manage such complex dependency graphs. Alright, enough theory for now. Let's take a closer look at the module decorator. In our coffees module, we declared coffee service in our providers array. So far, we've supplied all of our providers via a list of class names. But in fact, this syntax is actually a shorthand version of the more complete syntax. Now that we see this explicit construction, we can start to understand the dependency registration process. With this complete syntax, we can see that we are clearly associating the token, coffee service, with the class coffee service. The shorthand notation is merely a convenience to simplify the most common use case, where the token used to request an instance of a class comes by the same name. Later on in this chapter, we'll be looking at other useful ways to provide alternative values and other dependency injection tips and tricks. By default, Nest.js modules encapsulate their providers. This encapsulation makes it impossible to inject providers that are not either directly part of the current module or exported from a module being used. You can think of exported providers being your module's public interface or API. Let's look at an example of how this encapsulation works and how we can use it in our applications. Let's start off by defining a brand new coffee rating module. To generate a new module with the CLI, let's enter in nestgmo coffee-rating. We are using the nest CLI shorthand syntax here instead of the more verbose nest generate module. Now let's create a new provider called coffee rating service and encapsulate it within our new coffee rating module. To help us understand encapsulation better, let's say our new coffee rating service depends on coffee's service to fetch coffees from the database. We know that coffee's service belongs to a different module. So let's make sure we import the coffee's module here in our new coffee rating module. Switch over to coffee rating service and use the constructor-based injection to add the coffee service. If we switch to our terminal and try to run our application with npm run start dev, we'll notice that Nest won't be able to bootstrap properly and an error message will be thrown that says Nest cannot resolve dependencies of the coffee rating service. Please make sure that the argument coffee service at index 0 is available in the coffee rating module context. So what did we miss? Well, as we said a moment ago, all modules encapsulate their providers by default. That means that if you want to use them in another module, we must explicitly define them as exported, making them a part of the public API of that module. Alright, so this sounds like an easy fix. Let's open up the coffees module and add an exports array to the module definition, making sure we put coffee service inside of it. If we save our changes and head back to our terminal, we'll see our Nest application was able to bootstrap successfully, and we no longer see any errors. And that's encapsulation in a nutshell. Now we are able to use coffee service anywhere in our coffee rating module. As we can see, this encapsulation really gives us full control over what is public and privately available within our modules, and other modules that depend on them. What happens when our application's requirements go above and beyond what we've seen available with injecting and creating providers so far? Let's take a look at some example use cases where we might need something a bit more sophisticated. Let's say we are creating a custom instance of our provider instead of having Nest instantiate the class for us. Or let's say we want to reuse an existing class in a second dependency. How about if we want to override a class with a mock version for testing? And lastly, what if you want to use a strategy pattern in which we can provide an abstract class and interchange the real implementation, or actual class that is to be used, based on different conditions? Well, luckily Nest allows us to define custom providers to handle use cases such as these and many others. We saw in our previous lesson that when we add providers to our Nest modules providers array, it's really just a shorthand version of providing the token and providing what is to be injected in that token's place. Nest provides several ways of defining these custom providers. So let's walk through a few of them so we gain a deeper understanding of how we can utilize each one in our own applications. The first custom provider we'll look at is the useValue syntax. The useValue syntax is useful for injecting a constant value. Let's say we wanted to add an external library into the Nest container, or maybe we're replacing a real implementation of a service with a mock object. You can imagine for testing this would be ideal. Using our application as an example, let's say we would like to force Nest to use a mock coffee service for illustration purposes. Let's add our mock service implementation here that we'll use in this demo. Now, let's replace our coffee service in the providers array to our custom provider and use the useValue syntax. With what we just did, now whenever the coffee service token is resolved, it will point to the new mock coffee service anytime we inject coffee service in our application. So far in this course, we've used class names as our provider tokens. Remember that provider tokens are whatever we pass into the provide property. Sometimes we may want the flexibility to use strings or symbols as the dependency injection token. Let's say we provide a string value token coffee brands with useValue we learned about in the previous lesson and set the value to an array of strings. How could we use this provider in our application now? So far we've mostly seen how to inject a provider using the standard constructor-based injection pattern, like the one here. But for us to be able to use this standard pattern, it's required that the dependency is declared with a class name, because that is how Nest does a lookup for the dependency in the IOC container. Our coffee brand's custom provider uses a string value token. So how can we inject it? With these types of providers, we can simply use the inject decorator, which takes a single argument, being the token that needs to be looked up. Now we are able to use coffee brands and access that array of values we passed into this provider. It's important to point out here that while we directly use the string coffee brands inside the inject decorator, it is a best practice to define tokens in a separate file that can be used throughout the application. That way, we could simply import it here, avoiding costly mistakes such as typos or issues when we need to make changes or refactor our application in the future. So let's make a new file named coffees constants in our coffees directory. In our new file, let's add export const coffee brands. Now we can head into both our coffee service and coffee module and replace the string we were using and import this const instead. As you can see, we want to treat these string tokens as you typically would any other symbols, enums, etc., and define them in their own files so you can import them wherever they might be needed. For testing purposes, let's add a little console log in our coffee service constructor so we can make sure it's working properly. Let's open up our terminal and start up our application. And when it's finished building, we should see our array of strings show up. Another custom provider pattern is the useClass syntax. useClass allows us to dynamically determine a class that a token should resolve to. Let's take for example that we have an abstract or default config service class, and depending on the current environment, we need Nest to provide a different implementation of that configuration service for each one. Just like before, we'll provide our config service for the provider token, but for the value, we'll use the new useClass syntax. First, let's define some classes that we can use for illustration purposes. Since we want our config service to be different, depending on the environment, we are going to look at an example use cases where we can check our process env variable, node env in this demonstration, to decide which class to implement. Now, depending on what our node env is, config service will resolve to either development config service or production config service. Our next custom provider pattern is the useFactory, which is a very common and helpful pattern you will surely use many times in your application. The useFactory syntax allows us to create providers dynamically, which can be extremely useful if you need to base the provider's value on various other dependencies, values, etc. The value returned from the factory function is what will be used by the provider token. What makes these factory functions so special is that they themselves can inject other providers needed to compute the returning result. Let's look at the coffee brands provider we used in our previous lesson and convert it to useFactory. Let's start out by making it a function that simply returns the array of strings we previously had. For testing purposes, let's make sure we still have that console log in our coffee service here so we can make sure it's working properly. Let's open up our terminal with our application running, and we should see our array of strings still show up. Pretty straightforward, but we haven't taken full advantage of factory providers yet. Let's look at a more realistic example and inject some providers into it. First, let's define a random provider for illustration purposes, and make sure to register it as a provider. Now, let's update our existing coffee brands provider to use the coffee brands factory. In this code, we can see that we are using a new property for our providers called inject. Inject takes in an array of providers itself. These providers get passed into our useFactory function, and we can use them however we would like. This is just demonstration code, of course, but you can see we have a coffee brands factory that we are injecting into our useFactory function and calling a method on it. Although this is all pseudocode, what's important here is just knowing that you can use your dependencies here, doing whatever type of business logic you need, letting you return whatever values you want for this provider. Sometimes when our applications bootstrap, we need to delay the entire process until one or more asynchronous tasks have completed. Let's imagine a realistic scenario where we do not want to start accepting requests until the connection with our database has been established. This is exactly where asynchronous providers come in. To achieve this, all we need is to use async await in combination with the useFactory syntax we just saw in the last lesson. The factory function we pass to Nest can return a promise, allowing it to await any asynchronous tasks. Nest will await resolution of the promise before instantiating any class that depends on this provider. Using our coffee brands provider again, let's say that this provider's data has to be asynchronously queried from the database before it can be used anywhere. Let's go ahead and define our asynchronous provider by firstly adding the async keyword before our factory function. Just for illustration purposes, we'll add in some mock demo code next. Let's imagine we are injecting some sort of database connection, and then querying the database to get all of the coffee brands. But we are going to just resolve a mock promise with our array of brands, pretending that's our database connection and query, and return it back to the factory. For testing purposes, let's make sure we still have that console log in our coffee service here, so we can make sure it's working properly. Now, if we add console log in our factory function, save our changes, and open up the terminal, we'll see that our coffee service class is instantiated after coffee brands are returned from the database. Asynchronous providers make complex situations such as these that much easier. We no longer need to worry about race conditions and many other common application startup needs. So far, every Nest module we've seen has been a static module. Sometimes we need a little more flexibility when using a module. For example, static modules can't have their providers be configured by a module that is consuming it. So why does that matter? Well, let's consider a use case where we have a general purpose module that needs to behave differently in different circumstances. Think of this concept almost like a plugin system. Our dynamic modules require some configuration before they can be used by a consumer. To help us understand how dynamic modules work, let's create a database module that can be passed configuration settings before it instantiates. This is just for demonstration purposes, of course, since we have type_rem module already creating a connection to our database. First, let's generate this new module and call it database module by entering nestgmo database. Now, let's open it up and head over to the providers array and define a connection provider. Let's utilize the useValueProvider syntax we've learned and call the createConnection method from type_rem, passing in some arbitrary values to set up our database connection. Since our database module hardcodes these connection options, we can't easily share this module among different applications, can we? This is because our database module is statically configured and can be customized. What if another application wants to use this module, but it needs to use a different port? Well, lucky for us, using nested dynamic module features, we can let consuming modules use an API to control how this database module is customized when it's imported. To achieve this type of customization that other modules can control, let's define a static method named register on our database module like so. Now, let's step through the code we just added, one section at a time. First, we can see that our register method accepts options that consuming modules can pass into it. We've made our options take on the interface of connection options, from type rem in this case, which helps strongly type everything we are allowing other modules to pass in, the database type, host, password, etc. Next, we can see that our register method returns the type of dynamic module, which has essentially the same interface of our typical modules, but requires that a module property be passed, which we can see is just our current module, the database module itself. Aside from that, we are utilizing the providers array here to create that connection provider, but now we are able to pass down all the options we received when this register method was invoked. Let's make sure we delete the previous static implementation of connection above, and just like that, we've created the ability for our consuming modules to pass in exactly the connection options they need. With this in place, we can import our database module in other modules just like this. Since we have an interface for our options, we know every possible option we can pass down and their required type. This is an extremely important pattern to understand, as in most advanced Nest applications, it is used very often since many applications require this type of flexibility. For those of you coming from different programming language backgrounds, it might be unexpected to learn that in Nest, almost everything is shared across incoming requests. Remember that Node.js does not follow the request-response multi-threaded stateless model, in which every request is processed by a separate thread. Because of this, using singleton instances is fully safe for our applications. However, there are edge cases where you may need a provider to have a request-based lifetime for a certain desired behavior. Take for example applications that require instance request tracking or multi-tenant applications. Injection scopes mechanism allow to obtain the desired provider lifetime behavior you need. By default, every provider in Nest.js is a singleton. So as an example, when we use injectable in our coffee service, it's really a shorthand implementation for passing in an object with scope and scope default, the default being singleton, as the value. The instance lifetime of a provider is tied directly to our application's lifecycle. Once our application has bootstrapped, all singleton providers have been instantiated. As a best practice, using singleton scope is recommended for most use cases, most notably for performance reasons. Alright, so now that we've seen the default behavior, let's dive into two other lifetimes available for injectable providers. These are transient and request scoped lifetimes. Transient providers are not shared across consumers. Each consumer that injects a transient provider will receive a new dedicated instance of that provider. Let's say we change our coffee service to be scoped transient. Let's update the console log here inside our coffee service constructor to say coffee service instantiated, just so we can test and make sure this instantiated more than once in our application. Let's make note of the fact that our coffee service is being used in two spots, in Coffee's controller and Coffee brand's factory. Now, let's head to the terminal and start up the application. Once it's finished building, we can see that when our application started up, Coffee service instantiated shows up twice. If we remove the scope transient line from our injectable and head back to the terminal, we'll see Coffee service instantiated only appear once now. This is because our service is back to being a singleton again. To specify the scope of a custom provider, add an extra property named scope. Let's use our coffee brand's example from our previous lesson. If we add scope transient here, then we are all set, and it will work exactly like in our previous example. Our last scope lifetime option is known as request scope. Request scope provides a new instance of the provider exclusively for each incoming request. Note that the instance is also automatically garbage collected after the request has completed processing. To mark a provider as a request scope, simply pass in scope request into your injectable. Let's try it again on our coffee service, making sure we still have our console log in the constructor. And just like that, the coffee service will be instantiated on every request. In the next lesson, we'll dive even deeper into request scopes. See you there! We left off the last lesson discussing request scopes and how a new instance of the provider is created exclusively for each incoming request and garbage collected after the request has completed. To better understand request scoped providers, let's look at our coffee service again and make sure it's still request scoped. Let's double check that we still have that console log in our coffee service constructor so we know each time it has been created. With all of this in place, and our application running in the background, running npm run start dep if it isn't, we can see that even after our application bootstrapped, we didn't see any logs that our coffee service was instantiated, which is exactly what we should expect, since we haven't requested any API endpoints that use this service yet. Let's open Insomnia and execute 3 HTTP GET requests to our coffee's endpoint. Now, back to our terminal again. We can see that there are 3 messages logged saying coffee service instantiated, which means that this service was exclusively created for each request. Perfect. But wait a second. How is it even possible that coffee service was created 3 times, although our coffee's controller, which handles these endpoint requests, is a singleton, since we never change anything in the controller decorator for it? Well, in Nest, these scopes actually bubble up the injection chain. This means that if the coffee's controller depends on the coffee's service, which is request scoped, it implicitly becomes request scoped as well. To test this behavior, let's add a single console log to our coffee's controller constructor to have a verbose log in the terminal every time an instance of the coffee's controller class is created. Let's save our changes, head back to Insomnia, and execute those 3 GET requests again for the coffee's endpoint. Now we can see that there are 6 messages in our terminal, 3 from the service and 3 from the controller, which means that both were exclusively created for each request. Great! There is actually one more extra capability of request scope providers. Request scope providers can inject the original request object. This is useful if you need access to request-specific information, such as headers, cookies, IP addresses, etc. Note that with this great power comes great responsibility. Using request scope providers may have an impact on your application's performance. While Nest tries to cache as much metadata as possible, it will still have to create an instance of your class for each request. This might slightly slow down your average response time and overall benchmarking results. Unless a provider must be request scoped, it is always recommended that you use the default singleton scope whenever possible.